So this will finish out the notes for this unit. Remember, your test for this unit is when? Monday. I know, Monday test, okay? I'll give you the review tomorrow, and then if you want, I can wait and give it to you Thursday. You'll have class time on Thursday, but it will be due on Friday. Some practical applications of redox is, first of all, combustions are combustion reactions or redox. Anytime you see a free element by itself and it's free on one side and it's in a compound on another, that is a very good clue that that's going to be a redox, because it's going from a zero oxidation state to having a charge. And so in this case, really quickly, we see oxygen has its free element states and it's going into a compound. So that's going to be a redox, okay? If you want, we can figure out the charges of each one of those things and see how they change, or you can take my word for it. They're redox, okay? Do you want to figure out the charges?
Well,
That's a no.
there's no charges written on it there.
No, remember the oxidation states, remember? So that's a zero. So the fact that you know that it's in a compound over here is your clue. That's what I'm talking about. That's how you can recognize if something is a redox. If you see a free element by itself on one side and it's not a free element on the other side, then it's going to be a redox because it had to change.
Yeah.
Same thing here. This was a 0, and in this compound it's a +1, whereas this is a +2, and that's a 0. So that single replacement is a redox.
Wait, so double replacements?
Double replacements are not redox.
Are those the only ones?
Yeah, more or less for what we're
So
doing.
is redox something always has to be 0?
It doesn't have to be 0. There are other things that are redox. I'm just saying if you see a single element by itself on one side and not, that's a good way to recognize. No, like the one we did earlier, there were no free elements.
Okay.
I'm just saying that's a good way to recognize it. Okay?
Yeah, if I'm being honest, I forgot to watch the video last time.
Okay. All right. So also some synthesis and also some decomposition. Okay. Now when I say some synthesis, if I was taking, say, sodium hydroxide plus water and I get something else, that is still a synthesis, but that is not necessarily redox. So you got to check your charges. When in doubt, check if the charges change or the oxidation states, meaning they're like one number on one side. If they change numbers, then that's your clue that it's a redox. Okay. So there are some synthesis and decomposition that would not be redox, but some of them are. Okay. Electrochemistry is what we're going to mainly be talking about today. That's what we're going to be doing tomorrow in the lab, is some electrochemistry. And that is any conversion between chemical and electrical energy. It's an electrochemical process. Some of the examples in your body are nerve impulses. We have corrosion and electroplating. A lot of jewelry is electroplated. And so it makes it not turn yourself green or whatever. And then, of course, electrochemistry. Why that's on there twice, I'm not really sure. Guess I really wanted y'all to know that. It's not twice in your notes, is it?
It is, but it's a different.
Okay, I'm not sure.
It says the first one is any conversion between chemical and electrical energy is electrochemical process, but then the second one it says chemical reactions either release energy or absorb energy. Remember thermochemistry and redox the energies in the form of electricity.
Okay, so keep that definition. I just didn't do it right on here.
Examples, batteries and electrolysis.
Okay, so this is a reduction potential chart, okay? And what this is this is a published chart. I will get you guys a copy later. You don't need one today, but I will get you guys a copy later. And what it is it's literally listing all of the reduction or the standard ones we know, and it's listing them in order, and they're all reduction, okay? And so if we were wanting to know what one of these was as an oxidation, we would simply flip it around, and then we would flip the sign of the energy, okay? So in other words, if I'm oxidizing fluorine, instead of producing a positive 2.87 volts, it would require me to put in 2.87 volts to oxidize it instead of reduce it. So the thing you need to understand about this chart is they're all listed as reductions, okay? And if you need to do an oxidation with that, you flip it, okay? The ones at the top are the most likely to be reduced. The ones at the bottom are more likely to be oxidized, okay? And we'd flip them. So like you're not going to see fluorine oxidized. Because remember, oxidation is loss of electrons, right? So do you think fluorine, which is the most electronegative, do you think it's going to want to lose electrons?
Oh, but is it 1, 2?
No, it's not going to. Yeah. it's going to be the most likely, fluorine's the most likely to be reduced, therefore making it the least likely to be oxidized.
So is that every reduction?
No, it's just of some. There's more.
Okay.
Yeah, there's just some. Okay. So we're going to talk about voltaic cells. They're also called galvanic cells. You need to be able to recognize both words, and they are for processes that are spontaneous. And the way that we know that they're spontaneous is they generate a positive voltage. So a while ago when we were looking at that reduction potential, it was a positive voltage for fluorine to be reduced. Okay, it would be a negative voltage. So if we're talking something spontaneous, it's got a positive voltage. If it's not spontaneous, it's got a negative. Okay, meaning it's going to require you to put energy into the system. So these are some things you have to know. You've got your electrochemical cell on there. We're going to label it in just a second. A lot of it's already labeled. But the anode is where the oxidation occurs. We remember that by anox. Sorry about that. Anox for anode oxidation. This unit has a lot of acronyms to help you remember it. The cathode is where reduction takes place. We call that red cat for reduction cathode. Also, can remember the cathode is in a galvanic cell is positive. The salt bridge allows the ion flows to go back and forth because you can't have an uneven balance of ions. And then the way that the electrodes flow is they flow from the anode to the cathode, and we say that as fat cat, and that's because the cathode will get bigger. So write that down. Cathode gets bigger. And that's because the electrons, as they flow, it'll deposit things on the cathode.
Why does the salt bridge not have
It just doesn't. Because it can use different kinds of salt. Potassium nitrate is a very common one to use in there, but it helps balance out the electrons because you can't have it build up on one side or the other. So this is what our standard...
what happens if it does build, if you don't have a salt bridge?
The reaction... Well, first of all, if you don't have salt bridge, it won't happen. It won't. If you take that salt bridge out, the reaction doesn't happen.
All right.
Mm-hmm. Yeah. And at some point, the reaction becomes depleted because you run out of reactants, okay? But this particular one is showing the reaction of copper and zinc, and it's showing you the half reactions. So remember, anox is where anode is negative and cathode is positive. And then here's your electrons going this way. Anode to cathode, so fat cat. So if this reaction was to proceed, what would happen is eventually the zinc, you would be able to tell that it's disappearing or going into solution, and the copper would be getting bigger. You would plate it and get bigger and bigger. These are the half reactions down here, okay? Because they happen to be balanced with electrons, so it wouldn't require any balances. When we are writing them, and if you see some of the way that Miss Lawrence is having her kids do their half reaction, she's having them draw the line like between them to show oxidation and reduction. I don't know if y'all looked at any of theirs because I noticed it last night. I have you do it up on top of each other. I just think it makes it easier to add it up when you're ready to add it up. But if you see them doing it, it's not wrong the way we're doing it. It's not wrong the way they're doing it. It's just a different way to do it. I just think it's easier for y'all to add them up when you can see them.
Balance it because you get 2 negative on one side, 2 positive on the other.
It's balanced. Where is it not balanced?
Zinc plus 2 negative yields zinc 2 positive.
This is even charges over here. What are you talking about?
On the zinc one, it's 2 negative on the left because there's 2 electrons.
Two positive.
And 2 positive on the right because zinc.
Oh, I see. Because they're both showing you the reduction, and so one of those would actually be oxidized.
But it's not.
Yeah, but I'm saying it's not.
Yeah, I know. They're just showing you these are from the reduction potential chart. I see what you're saying.
So it's okay if they're not balanced.
Yeah. So when we would go to do the calculations with it, we would actually we would flip this around. Okay. Yeah, I know. But then when it does. Trust me.
All right, I'm gonna trust
I'll
on
go
this
back
one.
and look. It might be a mistake on the graph that I pulled up. I didn't look at
I'm
it
gonna
that
trust
closely.
on this one.
Okay.
Just know I'm confused. Because right now everything I want.
Yeah, you're right. That should be over here. I think they just listed it wrong.
They just listed it?
Yeah, they just listed it wrong. So let's change that.
Okay.
Put that.
Then we see-
Although, is that on yours that way? Did it print out?
It is on ours though.
Which one's over there? That is incorrect. Thanks for spotting that. I didn't even look at that when I was more concerned about the graph. Not the graph, this being labeled correctly and this being labeled correctly. When we're writing it as an electrochemical reaction, we actually write it like this down here. And we say the zinc, we always put the anode and the cathodes on the ends. And then we put what's in the middle, and then the double line right there, where I have the arrow, that's showing that there's a salt bridge. And that's the way we would show it. Now, if you go on to take AP Chem, electrochemistry is a fairly big unit. It's one of the last units we do, and you have to do calculations on figuring out how much volts and stuff like that. Okay. This is a voltmeter, so you could be measuring how much voltage that would be produced from this reaction, and using the reduction potential chart, we could figure out how much voltage would be produced. Okay. Which is how you would figure out if you're using a galvanic voltaic cell, or what we're fixing to talk about is an electrolytic cell. Okay?
Is that how battery works?
Yes.
Yeah.
Yeah. There we go. Examples of galvanic cells. Your car battery is a galvanic cell. There's the reaction down at the bottom. You don't have this graph in your notes. I just kind of wanted you to see. But a battery in your car absolutely works that way. Also, you have hydrogen fuel cells work that way too. You just have porous anode and a porous cathode. And then dry cell batteries, like your Duracell type batteries, they work that way as well. So they are a galvanic or a voltaic cell. Now, eventually they run out because you run out of reactants, but it'll work until you run out of reactants. Okay? And then the second type of cell is electrolytic cells. Okay? And they are for non-spontaneous reactions, which is what we're going to be doing in the lab tomorrow. And what are you supposed to bring for lab tomorrow? A shiny penny. Won't work with a quarter. Has to be a penny.
What about a $50?
Has to be a penny. If you want to do two, if you want to leave one silver and one air quotes gold, bring 2 pennies. You can. But if you want,
Are we actually making gold?
no. If I could actually make gold out of pennies, I would be not here.
How is
I'd be rich.
How is it turning gold?
That's why I say gold.
It's not actually.
It's not actually gold. It'll look gold, but it's not.
How's the color turning gold?
That's. Why don't you wait for tomorrow?
That's part of the lab.
That's what we're doing tomorrow. So examples of this are electroplating, electrorefining, and electrolysis. This is for non-spontaneous cells, so it has to have a power source. Okay, so write yourself a note, needs a power source. In this case, you can use a battery to force the reaction to happen, which is what we're going to be doing tomorrow. You'll come in and there'll be those little like box-looking 12-volt batteries, and that's what we're going to use to drive the reaction. Okay. So electroplating is an example of that. The oxidation is still occurring at the anode. The reduction is still occurring at the cathode, and they're still flowing anode to cathode. Difference is we got to force it to happen. And it's single cell, whereas the other one had double cells. We had anode and 2 separate ones. You'll see that it is actually happening all in one. Okay? She's cleaning up. She's putting up glassware. Now, the difference here, too, is while ago in the voltaic cell, the anode was negative and the cathode was positive. Look at it in an electrolytic.
Opposite.
The signs change because we're forcing it to happen.
So cations are not positive.
No, not cations, cathode. Different. Okay. All right, so let's look at some examples for that. There's example of electroplating, which is what we're going to be doing tomorrow. Okay? Only we're not going to be doing it with a spoon. We're going to do it with a penny. Okay? So we'll be using zinc as our anode, and copper will end up being our cathode. So what we're doing tomorrow would not, it won't happen unless you have the battery. You have to have the battery forcing the reaction to happen. Electrolysis is another example. That's where we can break down, say, water back into hydrogen and oxygen by running an electric current through it. And then electrorefining is a big part of industry where they want to have a pure metal. and they'll take out the impurities by doing that. And here's an example of impure copper, and they're changing it over to be pure. Take out some of the impurities, especially if you're doing mining an ore. You know what an ore is, right? O-R-E?
Yes.
OAR, like a boat?
No, O-R-E.
A boat.
Okay, sure. No. Okay?
Talking about a boat here, guys.
So, here's a handy little chart that I want you to write on left side,
Side, which one?
which would be page 180, 190.
Can we just write it on the back of the paper?
You can, because you don't keep your notebook anyway. But if you
Yeah,
keep your
I always-
notebook,
I always tell myself I'm gonna do it, but now my
so write this
cover-
on page 190.
cover
And
is
this is a
back.
really good thing to study for your test. Okay? So I'm going to stop the recording here, but y'all leave it up for you to copy.